Welcome to today's Explainer. Today, we're looking at what might just be the absolute most mind-bending contradiction in modern energy. On the surface, the technology we're going to examine sounds incredibly dangerous, almost like a massive engineering mistake. But as you'll see, it might actually be the key to safer, cheaper energy and a permanent solution to a decades-old environmental crisis. Okay, let's dive into this. Why on earth would anyone want to pump a highly explosive liquid through a nuclear reactor? I mean, in the nuclear world, safety is literally everything, so intentionally introducing a chemical that's famous for its violent explosive reactions seems completely absurd, right? Well, the idea behind this is actually incredibly well thought out. To understand why, we have to look at what's happening over in Wyoming. By the year 2028, a company called Terra plans to open the world's first nuclear waste-burning reactor right there in the US. Their goal is to deliver electricity for a staggering 5 cents per kilowatt hour, a price that could radically shrink your everyday energy bills. But more importantly, it's designed to completely destroy its own nuclear waste in the process. No long-lived radioactive components left behind to be buried in a mountain. Plus, it extracts 4 times more energy from conventional fuel. And the secret to this whole breakthrough? It's that extremely dangerous liquid we just mentioned.
That liquid is sodium, and it is a highly reactive, nasty material that engineers typically want to keep as far away from nuclear tech as humanly possible. Because when sodium simply touches water, it creates a massive, explosive reaction. It violently forms sodium hydroxide and hydrogen gas, releasing an immense amount of heat. That heat can instantly ignite the hydrogen gas, triggering a runaway chain reaction. It's pretty brutal.
So why use it? Well, a nuclear reactor fundamentally just splits atoms to generate heat, right? And you need a coolant to effectively transform that heat away, to actually make electricity. Traditionally, we use water. But to keep water liquid at the extreme temperatures inside a reactor, it has to be kept under immense pressure. Sodium, on the other hand, operates totally differently, and it comes with a couple of massive engineering advantages.
The first massive advantage is thermal conductivity. Liquid sodium is roughly 100 times more efficient at grabbing heat from the nuclear core than water is. Just to put that into perspective, while water's thermal conductivity is about 0.6 to 0.7 watts per meter Kelvin, liquid sodium sits at an incredible 65 to 85. This means it is exponentially more efficient at moving heat away, and that allows for far greater control and stability inside the reactor.
The second massive advantage is the boiling point. Water boils at 100 degrees Celsius. To stop it from boiling in a super-hot reactor, you need pipes built to withstand dangerously high pressure. If a pipe bursts, you've got a massive explosion risk on your hands. But sodium doesn't boil until 883 degrees Celsius. Because these new reactors operate around 500 to 550 degrees, the sodium stays perfectly liquid without any need for high pressure. There is virtually zero risk of a pressure-related pipe explosion. It is, ironically, quite tame, as long as it doesn't touch water.
Now, what's really interesting about this slide is how sodium impacts the actual nuclear physics. Inside a reactor, atoms split when they're hit by flying particles called neutrons. Fast neutrons are high-energy particles traveling at over 10,000 kilometers per second. And here is the absolute magic trick. At these incredible speeds, these fast neutrons are capable of breeding. That means they can literally transform hard-to-split nuclear waste into easily combustible fuel.
But here's the problem with traditional reactors. Water literally acts as a brake. When those high-speed neutrons hit water coolant, they get slowed way down to just 2.2 kilometers per second, becoming what we call thermal neutrons. In a normal reactor, you want this so you can safely split standard uranium. But at this slow speed, the neutrons completely lose their ability to activate and burn nuclear waste. Because sodium doesn't slow the neutrons down, it acts as a very weak moderator, the neutrons stay fast, and the reactor can actively recycle and destroy atomic waste.
Which brings us to the million-dollar engineering question. How do we safely use sodium without causing a catastrophic explosion? Because ultimately, to make electricity, that heat still has to boil water to turn a steam turbine, and if the sodium and the water meet, we have an absolute disaster.
TerraPower solves this with a genuinely brilliant 3-stage firewall. Instead of one single heat loop, there are 2 hermetically sealed loops. In step 1, the primary loop, the highly reactive sodium stays completely locked inside the reactor, extracting the heat. Then, it transfers that heat to a secondary loop. Finally, that secondary loop transfers the heat to the power generation stage to actually boil the water.
And this brilliantly illustrates the genius of the system. The secondary loop is made of molten salt, specifically a mixture of sodium and potassium nitrate.
This molten salt is a completely harmless buffer. It doesn't react violently with sodium, and it doesn't react violently with water. So this perfectly safe middleman just flows in pipes right past the water, generating the steam and ensuring the dangerous liquid sodium never even comes close to the power generation side of the plant.
But having this molten salt loop creates a massive, totally unintended plot twist. It's basically a Trojan horse. See, this isn't just a nuclear reactor anymore. It actually doubles as a massive battery for renewable energy. So how does this build into an incredible grid solution? Why is molten salt the ultimate battery? Well, because it has an incredibly high heat capacity and can simply be held in massive storage tanks. Traditional nuclear plants have to produce electricity constantly. They can't really easily ramp up and down. But with TerraPower's design, the reactor runs constantly, heating the salt. Then, that hot salt can be stored and used to make electricity later, completely on demand. If the wind stops blowing or the sun goes down, this system immediately steps in to fill the gap. And this flexibility allows for massive savings. Right now, integrating cheap wind and solar onto the grid requires expensive backup power plants or incredibly pricey storage systems just to cover those weather-dependent gaps. By acting as a flexible backup itself, this reactor design removes the need for those extra backup plants, potentially slashing overall electricity costs by 60 to 80%. Scientifically, it's a nearly perfect complement to renewables.
All right, moving on to Section 1, the trillion-dollar cost problem. Here is the financial projection for TerraPower's Wyoming plant. They project a cost of roughly $0.9 to $1.3 billion to build a reactor putting out 345 megawatts. This specific, highly optimized budget is exactly what allows them to confidently target that ultra-cheap 5 cents per kilowatt-hour electricity price. But let's look at recent history. Take the Hinkley Point project in the UK. The original projected cost was 21 billion euros. The current reality? It has ballooned to nearly 50 billion euros. The gap between theory and practice in nuclear construction is just notoriously vast. And it's not an isolated incident. Take this new plant project in France. It was originally budgeted for 3 billion euros. The actual cost, an astonishing 12 billion euros. These types of modern reactors have consistently only been economically viable because of heavy state support. So, the crucial point is that across the board, recent reactor projects have suffered massive 300 to 400% cost overruns compared to their initial forecasts. When construction costs multiply like this, it makes the actual price of the generated electricity 2 to 4 times more expensive. This is why many industry experts are looking at TerraPower's sub-$2 billion estimate with some pretty deep skepticism.
Which brings us to Section 2, the nuclear waste endgame.
Before we just write off the project due to budget fears, we have to look at the trump card of this technology. Storing toxic nuclear waste will cost us hundreds of billions of dollars over time. We currently have to safely secure, guard, and maintain deep geological storage facilities for incredibly long-lived radioactive materials. That is an ongoing, triple-digit billion-dollar black hole in global energy budgets. And that completely reframes the conversation. Even with massive budget overruns, eliminating our nuclear waste completely changes the economic math. Think about it. If the Wyoming reactor successfully works in 2028 and it safely destroys atomic waste, who cares if the electricity costs 5 cents or 20 cents? The astronomical savings of no longer having to manage and store toxic waste for millennia makes the initial construction price tag practically irrelevant. It ushers in a completely new era of atomic energy. And TerraPower is not the only company to realize this. A German company is already stepping into the ring, building a test facility in Rwanda right now. They claim their design is even cheaper, safer, and faster to build. In fact, their goal is to take Germany's existing stockpile of atomic waste and use it to power the entire country of Germany for 300 years. That's a milestone that would completely redefine global energy security for generations. Which leaves us with a final, thrilling question. Who will win the global race to finally burn our nuclear waste? We have an incredibly daring technological leap happening on 2 continents simultaneously. Will the American sodium-cooled approach take the crown in 2028, or will the German test facility in Rwanda get there first? Either way, the era of burying our atomic problems might finally be coming to an end. Keep an eye on this space, because energy is about to change forever. Thanks for joining me on this explainer, and keep asking questions.